x is equal to 0, because you have released after stretching the glider to a distance of x1 is equal to 0.1 meter. You release the glider from position of rest. So k1 is equal to 0. So I will put k1 is equal to 0. Okay. What is u1 grave? What is u1 grave? It will be mass of the glider m into acceleration due to gravity z and height from the ground. Suppose height from the ground is y. So it will be mzy. What will be u2 grave? What is u2 grave?
The same.
Same, because you are dealing with a horizontal surface. So potential energy is there, but the initial and the final potential energy are same. So they don't contribute much to this problem. So this is, so I can remove them. This potential energy is not, because they are same. So whether they are present or absent is not important for me. But this potential energy consists of two terms that you must understand. In this particular problem, because you are dealing with a horizontal surface, so you can afford not to write the gravitational potential energy. Okay, so I can remove this. Okay, now what you are going to find out? What is your purpose? What is your purpose?
Finding the velocity.
Finding the velocity of the glider when it is at a distance of 0.08 meter from the mean position. Okay, that means here. So, and where that v2x is there? In this k2. So I will write this k2 is equal to u1 el minus u2 el, u1 el minus u2 el. Automatically from there I will get back my v2x. Okay, so this is my physics equation, working formula. This k2 is equal to u1 el minus u2 el. So how I am going to do this? Yes, what should I write in place of k2? In place of
Half mv2x
half
square.
mv2 square, and here m is known and v2 square is an unknown quantity which actually I have to find out. So I will write half mv2 mv2x square, v2x square is equal to, what is u1 el? We have just learned it on Monday, I think. What is u1
Half
el?
kx1,
Half
half
x1,
k
Yes,
x1 x1.
half, then the spring constant k, and the initial position x1 square, Okay, similarly u2 el will be half kx2 square, half kx2 square. Now there is half here, there is half here, there is half here, and I am interested to find out my v2x. So first, so v2x is equal to k divided by m, that is x2 x1 square minus x2 square. So I can write it as x1 plus x2 into x1 minus x2. So that will make my algebra very simple. X1 minus x2, and this is v2x square, but I am interested to find out v2x, so I will take the square root. Okay, then I will just put the value. K is 5, m is 0.2, which is 1 by 5. So 5 into 5 will be 25. So k by m I will get 25, isn't it? Here I will get 25. What is x1? x1 is 0.1. What is x2? 0.8. So 0.1 plus, 0.08. So x1 plus x2 will be 0.18. So I will write it as 0.18. And what will be the value of x1 minus x2? So 0.1 minus 0.08 will be 0.02. So 0.02, isn't it? So I will be getting these things, and then the square root. If I do this algebra,
3.
yes,
So answer is 3.
answer is 3 or 0.3?
Zero point 3.
0.3. 0.
0.3. If you have seen the book, that is 0.3. If you have not seen the book, you have to calculate. Okay, so let me calculate, because I have made my algebra extremely simple. So the now calculation will also not be a big problem. Okay, first I will multiply this. I will write this 18 as 18 by 100 and 0.2 as 2 by 100. Then 18 into 2 will be 36, 36, and 100 into 100 will be 200, 10 to the power 4. So what I will be getting, you see, now everything has become very simple. 25, its square root will become 5. 18 into 2 will be 36. And then in the denominator, I have got multiplication of 200. So in the square root, I will get 100. 100 into 100. And then I will take the square root. So I need not require a calculator also. Square root of 25 is 5. Square root of 36 is 6, and square root of 200, 100 into 100 is 100. So 5 into 6 is 30, 30 by 100 is 3 by 10, and 3 by 10 is nothing but 0.30, 0.30 meter per second, isn't it? Meter per second. But you have got two signs. Signs means plus and minus, because both the roots will be, because v2x, so actually you have to add plus minus. Are you able to understand? So your answer will be both 0.30 meter per second, because mathematics shows you that both the answers are correct, 0.30 meter per second and minus 0.30 meter per second. This is what mathematics says. But physics says that now the glider is moving in the negative x-axis. So the answer will be minus 0.30 meter per second. Then why mathematics told you 0.30 meter per second? Because you cannot go to the mean position by avoiding this position while you are moving to the extreme position. When you are stretching this spring to 0.1 meter, you are passing this point. You see, you are passing this point. While you are stretching, actually the glider was passing this point, isn't it? And while returning also, it is passing the same point. That's why when you throw a stone, in the upward journey, the stone passes some point, and in the downward journey, the stone passes the same point. So the speed is same. The only difference is in the velocity. In the first case, the velocity was upward. In the second case, the velocity was downward. Exactly here also, while moving in the onward journey, the velocity was positive, that is plus 3.0 meter per second at that position, that is 0.08 meter, and while returning, its velocity is minus 0.30 meter per second. So did you understand?
Yes, sir.
Okay, so that is how you see the problem looks so complicated and so many parameters were there. But I have to understand what are the forces acting, other forces are not acting, situation is frictionless, so work done by other forces is zero. So and total mechanical energy is conserved. So I can write delta E is equal to 0, or U1 is equal to E2, E1 is equal to K1 plus U1, and E2 is equal to K2 plus U2. U1 consists of two terms, U1 gravitational and U1 elastic. But U1 gravitational and U2 gravitational are same because the surface is horizontal. So basically, finally, I will get K1 plus U elastic 1 is equal to K2 plus U elastic 2. Because you have started the glider from the position of rest, that's why K1 will be 0. So K2 is equal to U1 minus U2. Okay, then you have to do the algebra, and finally you will get two answers, plus 0.30 meter per second and minus 0.30 meter per second. But for this particular case, when the glider is moving in the negative x-axis, you have to ignore that plus 0.30 meter per second answer, and you have to mention that the velocity of the glider is 0 minus 0.30 meter per second, isn't it? So this is how, just by knowing the concept, we can understand the example, we can work out a problem involved with this kind of things. Now, this test your understanding 7.2 has a connection with figure 7, example 7.9, and which is not in this syllabus. So we will not take this test your understanding 7.2 now, but we will take it little bit later on. Okay. Now coming back to, probably I don't know, but as far as I have remembered, probably I was telling you about conservative and non-conservative forces. Whether I have told you or not, I have no idea. So just you have to say, because so many sections are there. So I sometimes forgot in which section where I left. Okay. So if you have remembered, we are particularly concerned with two types of forces. One is the gravitational force, which is associated with a gravitational potential energy. And another is the elastic force, which is also associated with a potential energy. The difference is gravitational force is constant and the spring or the elastic force is variable. So now the question is, if F a grave, that is the gravitational force, is equal to minus mg, and the gravitational potential energy is equal to mgy, is there a relationship between them? That is first question. And the second question is also same, that if F elastic is equal to minus kx and U elastic is equal to half kx square, is there a relationship between the elastic force and the elastic potential energy? And is there a relationship between the gravitational force and the gravitational potential energy? In order to understand that, let us take the derivative of the U grave. Okay, if U grave is a function of position, that you must understand. Either if it is a function, it can be a function of x, it can be a function of y, it can be a function of z. In two-dimensional, it can be a function of x, y, y, z, x, z. And in three-dimensional, it can be a function of x, y, z. So if suppose, let us assume it is a function of x, y, and z, then I will take the partial derivative. So the only difference is that here, instead of writing, so okay, so I will take partial derivative and I will write it, just wait. So I will remove this dy and oh, so let me write it. Okay, so here I will write u, and this u is a function of x, y, z, that you must understand. It is a function of x, it is a function of y, it is a function of z. Okay, that's why here also I will use the partial derivative, that when some function is a function of many variables and you are taking derivative of a particular one, then you have to use partial derivative. So you will get minus mg. Okay, so F, the y component of the force is this one, x component of the force is this one, and z component of the force is this one. So you can write the total force as minus I cap like this, and finally you will get this thing, F is equal to minus grade U. Do you know this symbol? Are you familiar with this symbol that I have used? A inverted triangle. Do you know this symbol? Are you familiar with this symbol? Hello? Are you familiar with this symbol? Yes. Are you able to see my screen or not? Hello? Are you able to see my screen?
Yes, sir.
So how I am getting my force from the potential energy? Have you seen how I am getting it? Any idea? If this partial derivative is bit problematic for you, we can take that, suppose this U gravity is function of only y, let us assume. This becomes very simple for you. It is a function of y only. Okay. Any idea? How can I get my F grade? How can I get minus mg from mgy? That is what my question. How can I get minus mg? Minus mg is my force. How can I get minus mg from mgy, which is potential energy, from mgy? Yes. So this is my question. How can I get minus mg from mgy? Yes. Anybody?
By derivative of u
By
cube
taking a
with
derivative.
respect to
By
y.
taking a derivative with respect to y, position derivative of the potential function. Okay.
But
So yes. So let us see what is happening. So I will take it.
So, but it's coming mg, not
Yes.
minus mg.
Yes.
So it is coming mg, not minus mg.
So first I will
By
take a derivative. So first let us take the derivative. We will go slowly. Okay. So I will take the derivative because now it is only a function of y. So I will take this derivative, and here I will put my u grave y, and I will write, let's see, uh, just wait. So I will put this here, and then du by dy mgy. So this I will put as here. I'll write mgy, and I will make this x as y with respect to y. Okay, this is also with respect to y. So finally, I will be getting mg. And you are correct, I am not getting minus mg. So what I will do, I will take a minus sign. I will take a minus sign. So I will take a minus sign. So I will get, there will not be any problem, and I will get minus mg. So I can write that f grave, because this is only one component. So I can write f grave or the y component. Okay, here also I can write y, because this is the y component, which will also be a function of y only. Okay, is equal to, so this will make you a little bit confusion, so let us don't put so many things, is equal to minus this one. I can write minus del q, control c, and I can write this one. Yes. So this is a very important result, that if the function, the conservative force, is always associated with a potential energy function, which, and you can always write f the force as the negative derivative, a special derivative. Special means not SPECIAL. I am talking SPATIAL. That means with respect to coordinate. Okay. So the special derivative of the potential energy, the negative special derivative of the potential energy function, gives the conservative force. And you can also, if you know the force, you can find out the potential energy function also by taking a integration, isn't it? U grave will be minus f dy. If you do the integration, then you will get u grave, and if you do a derivative, you will get the force. What I have told you is, I took this as only a function of y only. If my potential energy is a function of x, y, z, then I can find out many things, isn't it? That this is what I have find out. Del x means I have to make it mg x. So you see, I have found it out, and finally I have found out this is one-dimensional equation, and its three-dimensional equivalent is this one. I think you are familiar with this symbol. Do you know this delta symbol? This operator? This operator is called Nebula operator. This is the operator I have written. You look at the operator, isn't it? This is the operator, this delta operator. I think you are familiar with this symbol, isn't it? Are you familiar? Do you
no,
know this? Hmm?
No, sir.
No, okay. Probably you will learn it in mathematics that this is a three-dimensional derivative operator. This is del by del x or d by dx is a one-dimensional operator, and this is a three-dimensional operator. You see, this operator is equivalent to I cap del by del x plus j cap del by del y plus k cap del by del z. Now, this operator has three derivatives in it, with respect to x, with respect to y, with respect to z. Because if your potential energy is a function of x, y, and z, then you will get such equation, three such equations. F grab y is equal to minus del u by del y, f grab x is equal to minus del u by del x, f grab z is equal to minus del u by del z. And if you combine them, then you will get such an equations. You see, I have combined them because force is a vector quantity. That's why I have introduced I, j, and k. And finally, this vector operator, when it will operate on this u grave, then you will be getting your force back, isn't it? Similarly, if you look at this equation also, you will get the same thing. Your elastic force was minus kx and your elastic potential energy was half kx square. So if I take a derivative of, suppose I will take it, make it x actually, so that will be better. So del ul by del x. If u is a function of only x, then this partial derivative is not required. Otherwise, you have to require a partial derivative. Let us say that it is only a function of x only. So what I will do, I will take this and I will remove this. So d by dx, and here it will become x. Okay. So now you see your elastic is only a function of x. But if it is a function of x, y, and z, then you can write it as a different thing, isn't it? How you will write? Can anybody say? Suppose my elastic potential energy is a function of x, y, and z. So what will be my right hand side? Can anybody say? What will be my right hand side?
The partial derivative.
Hmm? Yes. What will be my right hand side? My right hand side will be UEL is equal to half kx square plus half ky square plus half kz square, and my F elastic will also be equal to minus I cap kx minus j cap ky minus k cap kz. This is how I will get my force vector, and I will get my potential energy like that. And when I will take the derivative, automatically I will get the force, isn't it? Which I have shown it here. And again, you can use that three-dimensional operator and you can write your conservative elastic force like this. So, looking at these two things, a variable conservative force like the elastic force and a constant conservative force like the gravitational force, we came to the conclusion that yes, we can find out the elastic force from the potential energy function by taking the special derivative of it. Special means with respect to position, which we have taken and we have found it out. And we can find out the potential energy function from the force by taking an integration, the reverse function, the reverse operation of, okay, this is how these things can be known. Now, the most important thing now we will discuss. Now, have you any idea how, suppose I want to find this relation, I want to study this relationship graphically. So anybody have any idea? How can I find out a graphical relationship of the gravitational force and the gravitational potential energy? Can anybody say? Suppose I want to study the gravitational force, let us say. First let us study the gravitational force, then we will go to the elastic force. Suppose I want to draw the diagram of my gravitational force. So what should I take? First I will take a two axis. Okay, one is the in this axis I will take my position y, and here I will take the force. the y component of the force. And what is my force? My force is Fy is equal to minus mg, because it is a constant force. It does not depend upon y. So it is minus mg. So it will be a straight line. Whatever the values of the y may be, it will be a straight line. So let me show. So this will be a straight line, this like this. So this is the graph of Fy. This is the graph of Fy is equal to minus mg, isn't it? Now tell me, what will be the graph of the potential energy function? What will be the potential energy function? Yes, can anybody say? Don't keep quiet. You have to continuously say something. Okay, suppose now I want to plot my potential energy is a function of one coordinate only. So y is along the horizontal axis and uy is along the vertical axis. Uy is my potential energy. What is the value of my potential energy? Anybody? Gravitational potential energy, what is its value?
The minus mg.
No, minus is not there. It is plus. It is plus.
Yes, plus
Okay,
mg.
uy is equal to mgy. Uy is equal to mgy. Now your potential energy depends upon y. When y is equal to 0, your potential energy is 0. When y is positive, your potential energy is positive. And it is linearly, it is like a straight line. Y is equal to mx form. It doesn't have any intercept. So it will pass through the origin. You must have the ability to interpret graph, isn't it? If you see, if this is like an equation of y is equal to mx, and what is the slope? The slope is mg, isn't it? So, and is there any intercept? No, it will pass through the origin. So, and it is linear because it has a slope. So it will look like this, it will go like this. And for y negative, it is minus mg. The slope is minus. That's why it has tilted in other direction. So this is the graph of u is equal to mgy. Okay, u is equal to mgy. And if I take the derivative of this graph mgy, I will get mg. And if I take the negative derivative, I will get minus mg, which is this one. So I can say that Fy, which is equal to minus mg, can be found out by the negative derivative of the potential energy function with respect to y, du by dy. So look at this, how beautifully you can find out. So this is the graph and this is the potential energy graph. Now we will go to the elastic force. So let me clear it. Now I will go to the elastic force. Okay. So first I will draw the elastic potential energy, or anything I can draw the elastic force also, no problem. And I can also draw the elastic potential energy. Now you can guess how the elastic potential energy curve will look like. Any guess? Any guess? How it will look like? So first let us draw the yes. Yes.
The parabolic.
Yes. Because it is this u is like ux. Suppose I will take ux. There is a square term that you must understand. Ux is equal to half kx square. So this is an equation to a parabola, isn't it? Because the presence of the square shows that for two values of x plus minus, you have got same value of u, and that can be got in a parabola, isn't it? So if I take x along the horizontal axis, ux along the vertical axis, so at x is equal to 0, you will get this value, isn't it? But for same x value, that is plus minus x, you will get the same u. So your equation, your graph will look like this, isn't it? You have got such a graph. This is your u is equal to half kx square graph. Okay. and your potential energy is 0, a minimum at x is equal to 0, isn't it? You look at this equation. At x is equal to 0, your potential energy is minimum, isn't it? At x is equal to 0, your potential energy was minimum. But what was the potential energy in the other graph? Potential energy decreases as y decreases in the earlier case. Here potential energy is 0 at x is equal to 0. For all y, Fy is less than 0, force pushes body towards decreasing y. That was the earlier case. Now I want to draw the elastic force diagram. So I will take x along horizontal axis and Fx along the vertical axis. Okay, and I have to draw Fx is equal to minus kx. Fx is equal to minus kx. This is very nice, actually crucial, because when x is negative, Fx is positive, and when x is positive, Fx is negative. So that can only happen for this graph starting from the third quadrant and in the fourth quadrant. Sorry, second and the fourth quadrant. It will lie, the slope is x. But when x is negative, you see, when you put x is negative, Fx becomes positive. So this is negative x, but positive x, positive Fx. When the x is positive, Fx is negative. So this is negative Fx. Okay. So and you will find out that this minus kx can also be found out by taking the derivative of u with respect to x and putting a negative sign before that. Du by dx minus is nothing but minus kx, isn't it? Minus kx, and that minus kx is your Fx. So the conservative force is very much associated with the potential energy function. Okay, they are inseparable. Whenever there is a conservative force, there must be a potential energy function. Whenever there is a potential energy function, there must be a conservative force. And very important is that because you are getting the conservative force just by taking the derivative of a potential energy function, and derivative are very simple mathematical operations. So this is one way of finding out the force from the potential energy function. In electricity magnetism, which you will read in chapter in your second semester, you will see that the Coulomb force is also a conservative force. So there must exist a Coulomb potential energy, and if you take a derivative of that Coulomb potential energy, you can find out the Coulomb force, and from the Coulomb force you can find out the electrical field. Okay, so this is how we can find out the we can establish the relationship between the conservative force and the potential energy, isn't it? So here also you can, this is for one dimensional I have told you, but you can use it in the 3 dimensions as I have written. That also you can find out. The only thing is that now your elastic potential will be a sum of 3 terms: half kx square, half ky square, half kz square. In the earlier case also, your potential energy will be a sum of 3 terms: mgx plus mgy plus mgz. That is like this is how you can find it out. Okay, so now what we will do, just let me find out. Probably we will do a, before going to the assignment exercises and the energy diagrams, which we will do in the next class, maybe I will be doing one problem for you. What is that problem? Example, I think, the last example of this chapter. That is example 7.14. So we will be doing 7.14. We have got still 10 minutes. And then in the coming class, we will do the assignments and the last topic, that is energy diagrams. Okay. So example 7.14, a puck with coordinates x, and y slides on a level, so horizontal, a level frictionless air hockey table, air hockey table. It is acted on by a conservative force described by the potential energy function. And the function is given as uxy uxy is equal to half k 1 by 2 kx square, a and then x square, ax square. Okay, so you are asked to find a vector expression for the force acting on the POC and find an expression for the magnitude of the force. Okay, so this is the, and this is probably, and this is the, and a and okay, so let me make this x little bit beautiful, this y also frictionless. Okay, so this is the problem. A POC with coordinates x and y slides on a level frictionless air hockey table, and it is acted on by a conservative force. Okay, it is acted on by a conservative force described by the potential energy function uxy is equal to half k. Oh, sorry. How can this be a function with only x? I have made a mistake. Just wait. Half kx square. Oh, sorry. Yes. Half kx square. Let us do it this way. Half k x square. This is x square. Okay. Plus y square. Plus y square. Okay, now can you say how can we proceed, how can we find out the force and the magnitude of the force? Yes. Yes, tell me, how can we do this?
Derivative.
We have to take the derivative. We have to take the derivative of the fx can be found out by the x derivative, fy can be found out from the y derivative. So what I will do, I will write fx is equal to, now I am doing the solution. Okay, solution. So what I will do, fx is equal to, I will write the x component as fx is equal to, isn't it, fx is equal to minus del u by del x. Okay, so I will put a minus here, minus, and I will put it here del u by del x. And what I will get, if I will take the derivative, I will get minus kx, isn't it? Similarly, I can find out my y component of the force. So I will find out fy is equal to minus del u by del y, and that will be minus ky. So I got my minus kx and I got my minus ky. Now I will find out the total force, isn't it? So the vector summation, the vector force will be, I will use it here. So now I will take my f here, and is equal to, I will put this kx minus kx, isn't it, minus kx, and then minus ky. Okay, this becomes y. I will n. Okay, but these are not vectors, so I have to introduce unit vectors. Okay, so I will unit one I cap here and one j cap here and one j cap here. Okay, one j cap here, or little amount of just readjustment of the term, and I can write it by taking this common, this minus I will take common, I put a bracket, just wait, C, I control X, I will put a bracket and I will write it, cake I can take common, isn't it? And inside the bracket I will keep this, this k is no more, this k is also no more, minus I have already taken outside, so this become my force. Now I am to find out the magnitude of the force, isn't it? Only F. So if I will find out the magnitude of this force, then what I am going to do, isn't it? So let us find out which was there here. Yes, so I can take this force. Okay, I will put it here. So this becomes its magnitude, and I can also call it just ordinary F only also, and that becomes square root of, as usual you can find it out as square root of minus kx square plus minus ky square, isn't it? So I will take a bracket here, and then 2 is here, minus kx inside the bracket, so here I will write minus kx. Okay, so minus kx squared, that is the x component, and then the y component also. Okay, so minus ky square. Okay, so this gives me the magnitude of the force is equal to, that becomes k square x square plus k square y square. K square will be taken outside, k, x square plus y square is r, so you will get kr, isn't it? Where r is equal to square root of x square plus y square. Okay, the position coordinate, where r is equal to square root of x square plus y square. Okay, this is true, this is x, and you can take this, say, plus y square. Okay, so this is how you can find out the magnitude of the force also from the given potential energy function, isn't it? So I think we have established the relationship of the conservative force with its associated potential energy function. We have worked out a numerical from the potential energy function was given, and we can find out the force, both its direction and magnitude. Okay, and in the next class we will do energy diagrams, which will give us many informations, and then maybe we will discuss the assignment exercises. Okay, so I think I should stop here. So okay, so thank you very much for your attention. Okay.